guys. So if you're here, that means that some of these nuclear decay equations are giving you a little trouble. Totally understandable. It's a little bit of an abstract idea. All right. So I'm going to try to help you get out a little bit. So what you need in front of you, right? ChemQuest number 84, that last page. All right, and we are going to look at number 4 and number 5, which will take us through several of those nuclear decay equations based on whether it's an alpha decay, a beta decay, or positron emission, electron capture. Okay? So, also, I think you're going to need a periodic table in front of you. So, hit pause real quick, go grab the periodic table so that you can kind of follow along what we're doing. All right? Speaking of periodic tables, I'm going to grab one. All right, back. Sorry about that, a little awkward. Anyways, so let's get started. So we're looking at number 4, all right? So in the case of number 4, we're gonna do 4 different things to a uranium atom, right? But in this case, we're not gonna take it through a chain of decays, right? We're just gonna try to see what happens to uranium if we do a beta decay. Then we'll take the same uranium isotope and see what happens if we do a positron decay. We'll take the same uranium atom and see what happens if we do an alpha decay, okay? Now, contrast that with number 5, in which case we're gonna take it through a whole chain of nuclear reactions, okay, to see how it goes through several mutations. That's probably more realistic of what actually happens in nature. But anyways, I feel like it's instructive to kind of do it both ways at this point. So, number 4, okay, we have uranium-238. 238 is its mass number. All uranium atoms have atomic number 92. All right. Now, notice that in the case of uranium here, we're not worried about whether it has a charge or not, right? Because the ionization of our atom isn't so important with our nuclear reaction. I'm sure there's some sort of weird little rule there, but it's not important for what we're doing. All right. So I should say 4A, by the way. I apologize if it says 4D. Sometimes the word formats things weird. But anyways, we want to do a beta decay. Okay? Now, with beta decay, sometimes we label that as beta minus, right? So you have to go back to your notes here, but what we have to understand with beta decay is we are doing an electron emission. So we're going to go minus 1 neutron plus 1 proton plus or minus 0 mass. Okay? So again, what you have to remember in the case of when we say a beta decay, all right, we have to know that means an electron emission. And when we emit an electron from the nucleus, we're essentially changing a neutron into a proton, which is where the minus 1 and the plus 1 comes from. And we do that by shedding an electron. Okay? So if I have uranium-238, 92 is what I'm going to start with. All right? Now, that is going to become a plus 1 in my atomic number because I'm adding 1 to my proton. So my bottom number is going to go from 92 to 93. Now, my mass stays the same. And if I look at my periodic table, this is where my periodic table is going to come in handy. I need to find, okay, I'm no longer going to be uranium because I have 1 more proton than I started with. Okay, so now I am Neptunian. So I'm going to put a little NP here. Okay, now what I also have to show in my decay equation is not just simply this transmutation. We have to show some conservation of matter here. All right, so what happened to cause this change? And in the case of beta decay, we went with 0, minus 1, E. And on the lecture, I told you guys if you just start remembering the symbols for electrons, positrons, and alpha particles. Okay? So this is the symbol for an electron. So this tells me that uranium-238 transmutated into Neptune neptunium-238 by shedding an electron or through beta decay. All right? So that's how I show that. Now, the next one, the B or E on your paper. Again, we're going to start with U-238. And in this case, we want to show a positron decay. Okay? So with a positron decay, we're essentially doing the opposite of what happened here. We're going to shed a positron instead of an electron. Now, positron decay or with electron capture, actually the same thing happens. We just do it two different ways. Okay? Instead of going up by one atomic number, I'm going to go -1 proton plus 1 neutron, right? Which by doing that, remember our mass is going to stay the same, so plus or minus 0 in mass. Okay? So to get that to happen, so U-230 or uranium-238, I'm going to subtract the protons. This is going to become 91. Mass is going to stay the same. And rather than having neptunium, I'm going to have palladium, which is the element right before, I'm sorry, protactinium, not palladium. So that's Pa. All right. Now, what particle was emitted from a nucleus or attracted to a nucleus in order to make this happen? It says it was positron decay. So it's going to be a 0, 1e. All right. So the distinguishing factor between an electron and a positron in terms of symbol, how we write the symbol, electrons have a negative charge, positrons have a positive charge. Okay? So this shows me the transmutation of uranium into protactinium by the shedding of a positron. Okay? There's C on the next one down. We're going to show an alpha decay. 238, 92, U. Now with alpha decay, so our big elements, like uranium, they undergo an alpha decay process, in which case they're going to break off chunks of their nucleus. So again, in terms of alpha decay, we are actually going to change the mass, right? So we're going to go -2 protons, -2 neutrons, -4 from our mass number. All right? So that's with an alpha decay. So this is our alpha decay. All right? So we're going to subtract 2 from our protons, which is going to make this 90. We're going to subtract 4 from 238, which will make this 234. I'm going to find number 90 on my periodic table, which is thorium. All right? Now, it's decay, right? So I'm getting rid of a particle. So what particle did I get rid of to make this happen? An alpha particle. And if you watched that lecture, you would know that an alpha particle is essentially a helium nucleus. So I'm going to write my mass number on top to show a loss of mass of 4. Write my other number at the bottom to show that I lost 2 protons. And that then makes this a helium nucleus. And there we go. There's an alpha decay equation. All right? And last but not least, B. Okay, again, I'm going to have not a decay, but an electron capture. Now, electron capture and positron decay, we will see the same thing happen from here to here. We're just going to show that it happened by a different process. All right? So, with electron capture, right? I'm going to go -1 proton plus 1 neutron plus or minus 0 in our mass, right? Our mass is not going to change unless we undergo an alpha decay, at least not significant. Okay? So, 238 and 2, U becomes 238, 91, PA. All right? Now, oops, I should have left more space there. Sorry about that. Because this is a capture, right? I'm not emitting anything. I'm going to write my plus on this side. Okay? So, in this case, I'm capturing an electron, right? So, what's the symbol for an electron? 0, -1, E becomes EA 23891. Okay? And those are the 4 types of decay equations you need to remember. All right? So, beta emission or electron emission, all right? Positron decay, electron capture, right? Again, electron capture and positron decay cause the same thing to happen. It just happens in a different way. And then, of course, alpha decay. What you also have to remember is what is our corresponding change in mass? What's the corresponding change in atomic number? All right? And the symbols for an electron, for a positron, for an alpha particle. All right? It just takes practice, time and practice. Okay? So we've got one more we'll do together, which is number 5, which is going to then take a starting element and then take it through several different types of decay, and that's called a decay chain, right? And so when we decay something like uranium, for example, it's going to go through a decay into something like thorium, and then thorium into something else, and then something else into something else. And maybe go through some positron emission along the way. There's lots of little decay steps in that chain, all right? And so number 5 is more representative of what we actually see happen in nature, okay? So I'm gonna grab an eraser real fast. All right, so for number 5, it says, what is the final symbol for the nucleus? All right, sorry, minor interruption there. Students, job would be so easy, so much easier if I didn't have students come here all the time, you know? All right, anyways, number 5 says, what is the final symbol for the nucleus formed by berkelium-247 after it undergoes alpha decay, then electron capture, then a beta, and then finally another alpha decay? All right, so we're going to take berkelium, transmutate it with an alpha decay, take whatever that is, go through a beta decay, take whatever that is, do a positron, okay, and finally another alpha decay, okay? So let's walk ourselves through. Let's just do berkelium-247. 247 over 97. It's a big element, right? So we would expect an alpha decay out of that anyways, right? It's first going to undergo an alpha decay. So it's a decay, which means our plus will be on the right side of that arrow, right? So what happens with an alpha decay? -4 from the mass, -2 from the atomic number. All right? So then you go to your periodic table, you find number 95, and that is americium. AM. Now, how did that happen? We shed an alpha particle. All right? So there's our alpha decay. Now, in the next step, we're going to begin with americium. Okay? Now, in this case, we're going to do an electron capture, all right? So because we're capturing that, that means we're going to add our plus to the left side. So decays, the plus goes on the right side of the arrow. Captures, the plus goes on the left side of the arrow. Okay? So I'm going to capture an electron. 0 - 1 E. All right? Now, what's going to happen with electron capture? We're going to increase our number of neutrons, decrease our number of protons. All right? So let's see this go down 1 to 94, but my mass will stay 243 because electrons are too small to really matter. All right? So then I go to my periodic table, I find number 94, and I will find that I have plutonium. Okay? So in the next step, I'm going to take plutonium. 94, 243, PU, right? And I'm going to do a beta decay of that. Okay? So in this case, what's going to happen with the beta decay, right? I am going to increase my number of protons by 1. Okay? So I'm going to go back to 243. This doesn't change to 95 AM plus 0 minus 1 e. That's a little weird to just reverse the process that just happened, huh? Oh well. And last but not least, another alpha. So I'm back to americium, 243, 95 AM. I'm going to do a decay, an alpha decay, right? Which means this is going to go down to 239. This is going to go down to 93. Find number 93 on my periodic table. And I will be at neptunium. And the P, oops, plus an alpha particle should be 4 over 2 H E. All right. Now, this would actually continue on through several more decay steps until it got this number down to less than 83. All right, and then we finally reach a stable, probably somewhere around lead or something like that. What would happen? Okay. So hopefully this tutorial was a little bit helpful for you, just kind of breaking down the thought processes that need to go in. But really, it comes down to when you see beta decay, you need to remember that's what happens when we shed an electron. All right. So every time there's a beta decay, you're going to have a plus 0 minus 1 e on the right side. All right. And what's going to happen to my atomic number with beta decay? What's going to happen to my mass? Okay. That's all you have to remember. And then you just use your periodic table to find the appropriate element that matches that atomic number. Okay? So with electron capture or positron emission, you just have to remember what happens to your atomic number, what happens to your mass, and recognize if it's electron capture, it's plus an electron on the left side. If it's positron emission, it's plus a positron on the right side, and their associated symbols. All right? And then alpha decay, minus 4 mass, minus 2 atomic number, symbol for an alpha particle, right? You subtract 4, subtract 2, find the element that matches that atomic number. There you go. Okay? So complex to begin with, but once you memorize a few important rules there for the different types of decay, not so bad. All right?